Bismillah ar-Rahman ar-Rahim. Our first limit is limit as n tends to infinity of n squared times integral x from 0 to 1 of the nth root of 1 plus x to the n minus 1. Note that this one is integral x from 0 to 1 of 1. This bracket is integral x from 0 to 1 of 1 plus x to the n, all to the power 1 over n minus 1. The binomial expansion of this part, minus 1, is summation over positive g of gamma of 1 plus 1 over n divided by gamma of 1 plus g times gamma of 1 plus 1 over n minus g. Then we have x to the power n all to the power g. This is the integrand. Note that g minus 1 over n plus 1 over n plus 1 minus g is equal to 1. We can apply the reflection rule for the gamma function to gamma of g minus 1 over n times gamma of 1 over n plus 1 minus g. This is equal to pi divided by the sine of pi times g minus 1 over n. This sign is sine by g cosine pi over n, that's 0, minus cosine by g times sine pi over n. Taking the reciprocal of both sides, we have 1 over gamma g minus 1 over n, gamma of 1 over n plus 1 minus g. This is equal to minus cosine by g is minus 1 to the power g minus 1. This is multiplied by sine pi over n. Downstairs we have pi. 1 over gamma of 1 plus 1 over n minus g can be replaced by minus 1 to the g minus 1 sine pi over n times gamma of g minus 1 over n, all divided by pi. We then integrate term by term. The integral is 1 over 1 plus nj. If we multiply by n squared, we can put an n here. We also get n sine pi over n over pi, which can be written as sine pi over n over pi over n. We are interested in the limit as n tends to infinity. Can we take the limit inside the sum? Rather than dealing with the gamma functions, let's go to the original form of the binomial expansion. When we integrate term by term, we have summation g from 1 to infinity. 1 over n choose g, 1 over ng plus 1. The magnitude of this binomial coefficient is equal to 1 over g factorial, 1 over n, 1 minus 1 over n, 2 minus 1 over n, all the way to g minus 1 over n. Without the magnitude, we have 1 over g factorial, 1 over n minus 1, 1 over n minus 2, and so forth. This is what we get when we have the absolute value. This bracket is upper bounded by 1. This bracket is upper bounded by 2. This bracket is upper bounded by g minus 1. On this magnitude, we have the upper bound 1 over g factorial, 1 over n times g minus 1 factorial. That's 1 over ng. The upper bound after multiplying by n squared is 1 over g, 1 over ng plus 1 times n. This can be further upper bounded by 1 over g, 1 over ng times n. That's 1 over g squared. Now we have an upper bound that depends only on the summation index g and not on n, the variable with respect to which we are taking the limit. Moreover, if we sum over positive g, we get pi squared over 6, which is a finite number. This means that we can apply the dominated convergence theorem. We can take the limit inside because the magnitude of the summand can be upper bounded by a function of g that does not depend on n, and the sum of the upper bound is finite. The question now is what happens to these terms as n tends to infinity. Sine of pi over n divided by pi over n, this tends to 1 as big N tends to infinity. Gamma of 1 plus 1 over n tends to gamma of 1, which is 1. Gamma of g minus 1 over n tends to gamma of g as n tends to infinity. N over ng plus 1 tends to 1 over g as n tends to infinity. So as n tends to infinity, the summand tends to minus 1 to the power g minus 1, 1 over g. Gamma of g divided by gamma of g plus 1 is 1 over g. The limit of interest is summation over positive g of minus 1 to the g minus 1 over g squared. Without the numerator, we have zeta of 2. Because of minus 1 to the g minus 1, we need to subtract double the sum of the reciprocals of the squares of the positive even integers. That's 1/4 of zeta of 2. So this summation is 1 minus 2 times 1 over 4 times zeta of 2. That's 1/2 of zeta of 2, pi squared over 12. N squared times minus 1 plus integral x from 0 to 1 of the nth root of 1 plus x to the n tends to pi squared over 12 as n tends to infinity. The second limit is limit as n tends to infinity of function g of n plus 1 minus g of n, where g of n is n to the power 3 over 2, e to the minus n over 2, the nth root of the product k from 1 to n of n choose k. We need first to investigate how g of n behaves asymptotically as n becomes very large. Specifically, we study the logarithm of g of n. When we take the logarithm, we get 3 log n over 2 minus n over 2 plus 1 over n summation k from 1 to n log n choose k. This logarithm is log n factorial minus log k factorial minus log n minus k factorial. If we apply the sum to log n factorial, we get n times log n factorial divided by n, that's log n factorial. We also get minus 1 over n, summation k from 1 to n log k factorial. Then a similar sum with k replaced by n minus k. In this sum, replace k by n minus k. We get summation k from 0 to n minus 1 log k factorial. Log 0 factorial is 0, so we can start the sum from 1. We can extend the sum to n. Then we need to subtract log n factorial. Now we have minus n over 2 plus 3 log n over 2. Then we have minus 2 over n summation k from 1 to n log k factorial. Finally, we have log n factorial plus log n factorial over n. Summation k from 1 to n log k factorial is equal to summation k from 1 to n summation g from 1 to k log j. Interchanging the order of summation, this is summation g from 1 to n log j, summation k from g to n of 1. This sum is n minus g plus 1. So this sum is summation g from 1 to n log j times n minus g plus 1. This is written here using the index k. We can split this to n plus 1 minus k minus 2 over n, that's 2k over n. We get plus 2 over n summation k from 1 to n k log k. We also have minus 2 over n times n plus 1 times summation k from 1 to n log k. This is log product k from 1 to n of k, which is n factorial. This quantity is minus 2 between brackets 1 plus 1 over n times log n factorial. These two terms together are minus between brackets 1 plus 1 over n log n factorial. To this summation, k from 1 to n k log k, we add n squared over 4 minus log n times this bracket. Here are these two new terms with opposite signs after multiplying by 2 over n. The goal of this step is to have a quantity that is the same as that in the expression of log a, the Glaisher Kinkelin's constant. Log a is in fact the limit of this bracket as n tends to infinity. We also have Stirling's approximation. The ratio of n factorial to e to the minus n, n to the n times the square root of 2 pi n, this ratio tends to 1 as n tends to infinity. Asymptotically, the quantity that we have is this part plus 2 log a over n, and this tends to 0 as n tends to infinity. This log n factorial is replaced by 1/2 log 2 pi plus 1/2 log n plus n log n minus n. After simplification, we find that log n to the power 3 over 2 e to the minus n over 2, the nth root of the product k from 1 to n of n choose k, this quantity is asymptotically equal to log n plus 1 minus log 2 pi over 2 plus a function of the order of log n over n. This tends to 0 as n tends to infinity. Asymptotically, this function of n is e to the log n plus 1 minus 1/2 times log 2 pi. Here is exactly the same function, replacing n by n plus 1. We can take e to the 1 minus 1/2 log 2 pi as a common factor. We get e to the log n plus 1, which is n plus 1, minus e to the log n, which is n. This bracket is equal to 1. And the limit is this exponential, which can be written as e divided by the square root of 2 pi.